Hi everyone, and welcome back to episode 2 of AI Unboxed. AI workloads are pushing data center networks beyond traditional designs, driving the need for higher bandwidth interconnect fabrics and software-defined networking, or SDN, to efficiently connect GPUs, storage, and distributed resources at scale. Today, we'll dive into interconnects and SDN, unpacking the key trends and challenges, and exploring the technologies and real-world strategies behind AI-ready networks. As always, we encourage you to share your questions in the Q&A panel as we go. Mike, over to you.
AI applications are hungry for bandwidth, and they're demanding higher scale, performance, and security from data center networks. As GPU clusters grow increasingly disaggregated, connectivity must be carefully secured to prevent data leakage risks. In this talk, Deepak Bansal, Corporate VP at Microsoft, explains how interconnect fabrics and SDN stacks in the cloud are evolving to meet the new needs of AI workloads.
So I'm super excited to be here, and as Michelle said, I'm going to be talking about interconnect fabrics and software-defined networking in the AI world. So as Praveen talked, AI is game changer for more and more applications, whether these are new applications or existing applications that are being made intelligent by incorporating AI into them. And it's impacting all industries: oil and gas, chemistry and natural sciences, of course, software development. There's almost no industry that at this point is not being impacted or revolutionized by AI. But when we look at AI is really at the heart of a larger cloud ecosystem. Customers access AI via applications that are hosted in the cloud, and these applications then call out into AI models that are also hosted in the cloud. So in that context, when we look at what AI cloud providers need to do to enable these AI or intelligent workloads, they need to provide private, secure, and reliable infrastructure, right, that enables users to access these AI applications that are hosted in the cloud. They need to provide flexibility for all the various kinds of workloads that are being made intelligent by incorporating AI into them. And lastly, scale. AI applications demand a lot of scale. There is just a lot of demand around AI, and so cloud providers need to provide tremendous scale, both regionally and globally. So let's look at what this means in terms of the interconnect fabric itself. As far as the network in the data centers is concerned, it's going through a massive evolution because of what the AI workloads are demanding from the data center fabric. First and foremost, we need high bandwidth and reliable networks. And I'll talk a lot more about high bandwidth in the next few slides. We need a low latency network to connect users to AI applications and to run those AI models. And we need those networks to provide security so that we can safeguard data and identity for users and applications. So at Microsoft, we have been doing a lot of innovation to drive higher bandwidth in the networks. And one such innovation is hollow core fiber. You may have heard about it. It turns out that speed of light is faster in air than in glass. So you can actually transmit data much faster by sending it through a fiber that is hollow in the inside. And that's essentially the idea behind hollow core fiber. It can give you 47% improvement in speed and much higher bandwidth and reliability. And at Microsoft, we are actually building hollow core fiber and deploying it to connect our data centers to each other, as well as inside the data centers itself, we are using hollow core fibers. OK, next, let's look at when we look at network inside the data center that is hosting AI workloads, right? There are two classes of networks that exist inside the data center these days. One is the front-end network that connects GPUs to CPUs and storage. And the second is the back-end network that connects GPUs to each other, right? Here, what I'm showing is the front-end network connecting the GPU parts or clusters to compute and storage. And what we are observing is the amount of bandwidth that is demanded off the front-end network has massively increased because of AI workloads. I remember couple decades ago when Praveen talked about how voice became free, right? And then video was coming out when YouTube happened, and we were talking about how video is going to drown out voice and any other traffic in the network. All that mattered was video that the network needed to support, and that was all the bytes. What has happened now is AI has drowned out video, right? The amount of data and bandwidth that AI is demanding is so much more that nothing else matters. We used to talk about 40 gig network, 100 gig network. Just a couple years ago, building a 100 gig network was state of the art. No more, right? 400 gig network is common, 800 gig networks are starting to happen, and we are talking about multi-terabits of bandwidth and capacity within the data center connecting compute clusters to GPU clusters to storage. And what is driving all this bandwidth is because the GPUs are processing large amounts of data that is being stored in storage, and this data is being accessed from the GPU clusters by compute as users are submitting natural language queries and whatnot. Next, when we look at the backend network, right, what has happened is because the GPUs are such cost intensive and so bandwidth hungry, we have built these specialized networks, the NVLink network, which is a scale-up network in a rack connecting few GPUs to each other, and a scale-out network, which happens to be the InfiniBand network right now, but moving quickly towards Ethernet, that is connecting multiple racks of GPUs and forming this very high bandwidth backend network to support both training and inferencing workloads. And when we look at the traffic that's flowing on this backend network, it consists of long-lasted and large flows, right? It's a lot of synchronous traffic because all the GPUs need to communicate weights to each other between each successive epochs, and then any delay in those weights getting communicated leads to GPUs sitting idle because they all need to be synchronized before they can run the next epoch. What that means is that the traffic is very bursty, and traffic or the performance of the cluster is determined by the slowest guy, right? Any unreliable network costs millions of dollars because that's how long the GPUs are waiting for the data itself. So the network has to become super, super reliable. The flows are flat flows and long-lived flows. So it's the traditional packet or traditional ways to load balance traffic on the network. ECMP actually is no longer effective because these are fat flows and they will overwhelm any single path. So we have to innovate and invest in new ways to distribute traffic through the network. In addition, when we look at a large GPU cluster, it may contain more than 100,000 GPUs now, and even more going forward. Building out such a large network itself is challenging if it has to be super high reliable, like I touched upon in the previous slide, right? Any instability, like if there are any heat and cooling issues, they will severely impact the performance of such a cluster. So Microsoft is making innovations in that space and contributing to OCP. We have massive amount of automation to drive defect-free build-outs because the wiring has to be correct with 100% reliability, and there are lots and lots of wires in these data centers. In addition, links will go bad, right? When you're running your training or inference workloads, links or switches, hardware devices will fail. So it's super important when failures happen that you're able to detect those failures very quickly and be able to repair those failures in real time. A human cannot be involved in the loop for maintaining a network at this high reliability. So what we have done is we have invested in streaming telemetry from the network in real time and then leveraging AI to automatically detect when the failures are happening and to be able to trigger repair actions. Repair actions here may involve routing around the failure, right? Taking out the bad element out of the network, right? But you cannot rely on a human doing that anymore because any delays here impacts your training completion time or impacts inferencing. Another key investment that we're making in this space is connecting GPUs to storage and to compute, right? These GPUs, by the way, may be distributed all across the world, right? We have third-party sites that we are getting GPUs from, right? So they may not be even in our data centers, and they are connecting to storage and compute that may be hosted in a data center in a different region altogether. And the amount of bandwidth that we need to provide connecting these GPUs to remote storage or to remote CPUs is of the order of multi-terabits per second. And this traffic needs to be connected privately from the GPUs to where the data is located. So we have been investing heavily in DPUs, data processing units, that you may not be, some of you may not be aware of. These are dedicated chips that are optimized for data handling and storage traffic handling. By leveraging DPUs in what we call network appliances. So these are farm of DPUs that we deploy that route traffic from GPU clusters to storage. And by leveraging DPUs, we are able to provide line rate private connectivity and advanced network services. And thereby, we are able to maintain high throughput connecting GPUs to the rest of the cloud infrastructure. An evolution of the DPU that we've been working on with many players in the industry is what we call smart switch. So rather than having DPUs deployed in these racks, you can buy a smart switch which will have DPUs inserted in them. And by leveraging these DPUs in the smart switches, you're able to do a lot of network traffic processing at line rate in the switches themselves without having to route them through these separate appliances and whatnot. So what we see is that DPUs become a fundamental infrastructure component in these AI data centers going forward. And by embedding these DPUs in smart switches, we are essentially making the network intelligent and enabling the network to provide advanced network services that are needed for these AI workloads. Now, I've talked a lot about the infrastructure, how the infrastructure in the data centers is evolving to support these AI workloads. Let me spend a little bit of time talking about the middleware, the software network layer that sits above the infrastructure. And over there, most of the AI applications are cloud native, right? So they are Kubernetes-based applications. And you need a very high performance network stack running on Kubernetes. So we have invested in what we call Azure Managed Container Network Interface. It's a Cilium-based software stack that is able to provide that network virtualization that is needed by AI workloads. It is able to provide advanced layer 3 to layer 7 policies that are needed to secure the traffic. We are also investing significantly in observability. Network observability becomes very fundamental because, again, any failure that happens needs to be found out in real time and addressed in real time. And then operationally, it has to be super simple. So let me dig a little bit deeper into what Azure CNI is and what it provides. So Azure CNI is like, for those of you who are familiar with the Kubernetes stack, it's a Kubernetes provides a pluggable interface into which you can plug in various networking virtualization technologies, and Azure CNI provides one such virtualization technology that is able to integrate with the offload technologies, the DPUs, so SmartNICs and the DPUs that are part of the AI infrastructure, and thereby provide high-speed connectivity at the virtualized layer to applications. In addition, we have done work in open source under the project name Retina, where we are able to provide rich observability for the network traffic in the data centers. Another area that is seeing rapid evolution in the network services space is load balancing. Traditionally, like for last 20 years, load balancing has been more or less standard, right? You get web traffic, you route connections, you monitor the CPU usage or the memory usage, and you do load balancing across servers. But in the AI world, we have to rethink how we do load balancing, because the way AI workload demands different kind of characteristics from a load balancer, right? When you have multiple prompts coming in from the same user and have a shared context, then you want to route those prompts to the same GPU or GPU fleet in the backend, so you have to be prompt aware. Similarly, when we think about caching, right, your traditional URL and content caching is no longer sufficient. You have to start thinking about semantic caching, because a lot of queries may be very similar. And if those queries are very similar, you don't want to be sending those queries independently to the backend, because as Praveen talked about, tokens are expensive, right? You don't want to be anchoring those high cost queries again and again to your inferencing backend. You want to cache the prompts and use semantic caching to be able to provide higher performance and lower cost for your AI workloads. So even in the security space, AI is putting different kinds of demands. Praveen talked about prompt attacks, right? So your traditional firewalls and web application firewalls, which worked for your traditional workloads, are no longer sufficient. And you need to think about how they need to be changed or improved now in the AI world and become prompt aware, so that they can provide these kind of firewalling capabilities for AI workloads. Okay, another area I mentioned that was super important is security, and we have invested a lot in ensuring that all your data is your customer is able to secure by building a network perimeter around your data and your model and your compute. So this is a virtualized perimeter that you can define around all your real estate that makes up your AI workload. Let me conclude by summarizing the various things that I've discussed, right? So high performance and security are critical for the network for AI. We providing a dedicated low latency WAN and low latency network is super critical. Providing this infrastructure that is optimized for AI, and then applications that are able to leverage that infrastructure is super critical. And then providing high frequency telemetry so that the workloads can run reliably and the network faults are recovered faster. Okay, I'm over time, so let me conclude there that there's a lot of investment and a lot of innovation happening in the infrastructure, in the interconnect that we are delivering to our customers to build their future with us on our cloud. And I look forward to partnering with the entire industry to help us build that infrastructure. Thank you.
Welcome back, and thanks for joining us. AI infrastructure is scaling at an unprecedented pace. What used to be 7 to 8 year network transitions are now happening in just 2 to 3 years, as the industry races from 800 gigabit and 1.6 terabit networks to lay the groundwork for 3.2 terabit networks. And this shift is about far more than faster speeds. It has system-wide implications across silicon, optics, interconnects, power, and economics in modern AI data centers. In this next conversation, leaders from Keysight will share their perspective on the biggest challenges teams face today, how compressed design cycles are reshaping the industry, and what it takes to deliver performance, reliability, and ROI as AI networks continue to accelerate. Take it away, Michelle.
Welcome. We are about to talk with Joachim Peerlings and Ram Periyakaruppan, the co-leaders of Keysight's AI Data Center Solutions. And we're going to listen to their insights on cutting-edge AI technology. All right, let's get started. Scaling interconnects and high-speed networks to 1.6T and 3.2T, it's not just an engineering problem, right? It has a system-wide impact on AI data centers. So tell us, what are the biggest challenges that teams face today?
For 1.6T based on 200 gig per lane, that will be deployed next year. And the key challenge will be to roll that out in volume, cost effectively and in quality. And then moving to 3.2T based on 400 gig per lane, that's a whole different challenge, particularly around signal integrity and developing the fundamental SerDes technology for that next speed class.
Yeah, and I think, as Joachim was saying, right, there's a huge leap that has happened when going from 100 gig per lane to 200 gig per lane. And as a result, design margins are shrinking. So I think engineering teams out there that are, building new PCB designs, routing these signals, as Joachim was saying, at 200 gig speeds is a big challenge right now, I think, that the industry is grappling with. And, again, they're looking at many different alternate technologies to, reduce power, looking at co-packaged optics, that together with silicon photonics, and looking at, all the optical interconnects that need to happen at these speeds. So I think, as with any new leap, the industry takes a while to, mature. And this covers from early stage design all the way to production ramp, as Joachim was talking about. So I think that, with time, the process will mature and the yields will improve. But right now, I still see that as a struggle. And I still see, a lot of time going into maturing the processes involved with moving to 200 gig per lane and 1.6 terabit.
Yeah. And then, when you go from 1.6 terabit to 3.2 and 400 gig per lane, you mentioned co-packaged optics, that's a choice for 400 gig per lane as well. But at 1.6T, you also have the choice of linear pluggable optics, so where you can do pluggable optics without a DSP or only a DSP in the transmit path, so half retime. And that option will not be there for 400 gig per lane because electrical and optical modulation will be different. So co-packaged optics is possible, but not the linear pluggable. So I think you can look at it, you have less choices as you evolve in speed, then your different choices are limited, and that will be a challenge moving forward.
Clearly, there are challenges, but reasons to be positive about it.
Certainly.
That's
certainly.
great. Well, AI infrastructure spans from pre-silicon simulation to real-time traffic in production networks. So can you walk us through the development lifecycle for interconnects and high-speed networking systems?
So it typically starts with developing silicon, so the SerDes technology, switching silicon, DSPs, and then the optics. And, that is the optical modules components, modulator amplifier drivers, TIAs, so a lot of components on the optical side need to be developed in parallel with a silicon.
And once that underlying foundational blocks, the physical layer is all coming together and maturing, then you have silicon vendors that need to build, switching chips, they need to build PHY chips, they need to build all types of silicon that go in this, massive AI infrastructure. On top of that, you have the system integrators that need to build the systems that use all these components that, interconnect everything. So it's amazing how all of this comes together in the industry. But, I think the key thing with that AI has triggered is a compression of these design cycles and really forcing the industry to have to innovate at a much, much faster cycle than they are normally used to. And it's an exciting time for all of us to participate in that.
And if you look at the development cycle, so, I mentioned you first start with silicon and the underlying technology. And even before you start with developing that underlying technology, designers use our tools just to do fundamental research. And for 448 gig, for example, one of the key questions was, what modulation scheme would you use? And you could use, for example, our pattern generators and real-time or sampling scopes and put a simple baud trace in between, and you could get a lot of fundamentals done to see, how is a signal impacted by a certain trace length, and, what modulation formats has what compromises. And that's typically one of the first steps that designers use. And then they start designing silicon. We need to test the silicon TX, RX independently. You have interoperability between components and the silicon. and then later when it goes into the network, each component has been validated.
Right, and once each component has been validated, I think the fundamental, difference with AI is that it's all about systems, right? And how do you get all of these components? Like you have hundreds of these components or thousands of these components getting deployed in a data center. They all have to talk to each other, and they all have to do it efficiently. And that's the challenge of AI. It's no longer about a single device. And so, yes, you do need those components to be, at their optimal best, but then you need all of them to work amongst each other, thousands of them.
Well, given the speed of innovation, like you keep saying, many networking and interconnect teams cannot afford to wait for full silicon. So how are organizations accelerating their development?
So I think, what's happened right now is, as you rightly pointed out, right, people can't wait. And a lot of things are shifting earlier into the R&D cycle, earlier into the design phase. So starting as early as when the silicon is being designed. And as I was just mentioning, AI is about systems, right? And that's fundamentally what's changed. It's about systems. It's no longer sufficient to just look at the design of the chip in isolation. It's important to look at that design in the context of how it would interoperate with thousands of other such chips. But the problem is, the designers don't have that. They only have one chip that they're designing. So that's where, we help the industry to be able to, emulate all those hundreds or thousands of other chips to surround that one chip early in the design cycle so they can validate that. That avoids, costly escapes, design escapes or bug escapes as they tape out the chip. And once the silicon comes back, we help them do the same validation in post-silicon phase, right? Like you had a pre-silicon phase, you do it in a post-silicon phase. And in the post-silicon phase, we surround that one real chip with thousands of other emulated chips, and they really are able to stress it at an AI system scale before they, then are confident enough to roll it out to production and deploy it in a real data center where they know it's going to work because they have the confidence of having done all of this in a pre and post silicon phase.
Could you give you one other example? If you, develop a new speed class, you have the silicon chips and you have the optics. And, you can develop the optics before the silicon is available. And how you can do that is like use our arbitrary waveform generator together with a sampling scope, with an oscilloscope, and then put the modulator between the equipment, and you can already assess, is the bandwidth sufficient? What about nonlinearities of your modulator? If you look at the RX subassembly, you can see what kind of equalization you need. So all that development can be done already before the silicon is available. And then when that arrives, you have minimum effort to integrate the whole silicon and the optical components.
Minimum effort. That's a relative term, perhaps. That's wonderful.
But time to market is money. So I think, the alternative is you wait for the silicon to come back and start with the optics. That takes you another 6 to 8 months.
You're going to miss the boat.
Yeah, right.
Joachim said you're going to miss the boat.
Yeah. Okay, let's keep moving. So after design, complexity compounds when validating full-scale, high-speed links across the network fabric. How are teams approaching system-level validation of interconnects?
I think the first thing is, you have to be able to replicate what's happening in a production environment in the lab, okay? And so we've worked, together with the industry on, getting the visibility of what's happening in a production data center and being able to capture that in the form of traces and bring that back into the lab and to recreate those same types of AI workload patterns at system scale. And the key here is, again, being able to, set up that, let's say system fabric and, replicate the same type of, stimulus that you see in a production data center in that lab environment to really, stress the components that are involved end to end and to be able to really push to drive optimal efficiency. The biggest challenge with AI is that everything might work, but if it doesn't work efficiently, you're wasting a lot of very, very, very precious resources, whether that's GPUs or whether that is all of the other billions of dollars that is being spent to, build out this infrastructure. So operators the large-scale operators that run these huge AI data centers are really focusing on, things at the component level, all of the optics, the interconnects, but also at the system level to drive optimal efficiency.
So network performance at 3.2T depends heavily on modulation choices at the physical layer. So what's your perspective on PAM4, PAM6, and PAM8 for 448 or 896 gigabits per second per lane?
The optics will be modulated with PAM4, and then there are two choices. One is co-packaging the optics with a silicon. Then you have PAM4 on the electrical side and PAM4 on the optical side, kind of a linear drive architecture. And then when you use pluggable optics at 400 gig per lane, the industry is converging on PAM6 on the electrical layer and PAM4 optical. Some are still exploring PAM8. Now, if you look at the next speed class, it's a big question. Will we double the speed again, or will we settle somewhere in between 600 gigabit per second, for example? It will definitely be a challenge, especially for the physical layer to get the next speed class done, and co-packaging the optics with, as short as a link you can get on the copper side is definitely a way to go for that next speed class.
Well, forward error correction, or FEC, is critical in reducing packet loss. So how are engineers balancing the latency, overhead, and power in networking gear?
Ever since we introduced 100 gigabit per Ethernet, FEC has been a critical part of that shift because of, errors. Bit errors are inherent and you can't avoid them, but having FEC has helped to alleviate a lot of the problems with, corruption and packet loss and so forth. And so FEC has been instrumental in that. Forward error correction has been instrumental. And so the subsequent speeds of 400 gigabit Ethernet, 800 gigabit Ethernet, and now 1.6 terabit all have a FEC block, right? And but now with AI, as with lots of things change, the industry is pushing for something called low latency FEC, where they are compressing, the FEC headers so that it's smaller and the latency involved in communicating data between GPUs can be done faster and quicker. One of the things that's happened with the transition from 800 gigabit Ethernet to 1.6 terabit is the advent of symbol mux versus bit mux. So everything up to now, up to 800 gigabit Ethernet speeds, was the way the framing was done on the physical layer was through bit mux, and now with symbol mux, what it ends up again doing is spreading the errors across multiple lanes instead of bursty errors on a single lane, and it helps again reduce the probability of a errored packet, right? And so all of these techniques are being brought to market so that we can ultimately get a packet from point A to point B as reliably as possible and as quickly as possible. So it's really fascinating to see how technology is evolving to cater to the needs of the market. But it's what's happening with FEC, and it's here to stay.
Pushing toward 3.2T pushes every single part of the networking stack to its limit. So I've got to ask, what breaks first at these speeds?
I would say that signal integrity is the hardest part. If you look at channel loss, connector performance, that's challenging, not on the optics, but even more so on the electrical side, and developing that fundamental SerDes technology for that next speed class 400 gig per lane for 3.2T. That will be one of the hardest parts.
And I think once you get the physical layer and the signal integrity, as Joachim was saying, sorted out, then as you start to build the switching, forwarding packets at 3.2 terabits per second, it's mind-boggling, right? And nowadays you have 102.4 terabit switches, and now that's probably going to double to 204.8 with 3.2T. The amount of data that needs to be processed and forwarded to the right destinations and made sure it's done in a proper way is just mind-boggling. So I think all of these challenges in terms of looking at things of reliable communication end to end, both from within the rack, which is traditionally referred to as scale-up networking, and across racks, which is scale-out networking. Getting all of these interconnects working reliably at those speeds will definitely be a challenge the industry will have to overcome.
The industry is racing towards 3.2T Ethernet for AI clusters and hyperscale networks. We've established that. But what is the timing there? When do you see this technology really advancing and starting to get deployed? If you could look in your crystal ball, what do you think? What do you see?
I would say technology and chips will be available in the 2027 timeframe, and then deployment, maybe sampling 2028, and then deployment 28, 29 is what I would say.
I would agree to what Joachim said there. I think right now what I'll say is that the hyperscalers are driving and dictating the timelines for the industry, and there's a rush. It's literally an AI arms race to get there as quickly as possible. And there's billions of dollars that they're spending and infusing into the ecosystem to try to get to these advanced speeds. So we're just kind of getting ready to start to deploy 1.6T, and we're already talking about 3.2. So what used to be sometimes 7 or 8 year design cycles before in between speeds has now, I think you'd agree, Joachim, maybe has compressed down to like a couple of years, 2-3 years, right, between major speed upgrades, right? So it's all of the technology that goes into it, the electrical side, the optical side, the switching side, the servers, the interconnects, the cables, everything has to get upgraded in that 2-3 year design cycle. And that's, the key challenge.
Yeah. And however, at the end of the day, it's also all about economics. So cost per bit, power per bit, that equation still needs to hold true for those new technologies to scale. And I think that's a real challenge.
That's true. We're going to go back to that in just a second, but I have to ask, is 6.4T really possible, or are we going to hit a wall?
I think, everybody said that we, hit a wall, many times again. And on the weekend, I, saw somebody wearing a T-shirt that said, it's all delusional until it works. I think that reflects the spirit of this industry. NTT Innovative Devices, they have a 6.4 terabit optical engine in their program. However, that is 32 times 200 gig, so still on the 200 gig per lane technology. To see true 6.4 terabit, like 8 times 800, it's probably beyond this decade.
But what I will add is the following, right? Ethernet has been with us for maybe about 50 years right now, since the origins back in 1973. And at the time, you started off with things like 1 megabit per second. So believe it or not, in this 50 years since that 1 megabit per second, we've advanced the speeds 1.6 million times. Okay, we've gotten faster by 1.6 million times. And as Joachim referred to earlier, right, the industry has been able to keep the cost per bit and power per bit, fairly steady in that time while advancing innovation and technology by a factor of 1.6 million x. So that's the staying power of Ethernet, and why it's been so prevalent in the industry, and it's permeated, and it has such a long staying power, right? So I think that, as much as we think that the industry might hit a wall or something like that, I think we've thought that many times before, and somehow everyone comes together and figures out a way to overcome it. And I'm pretty confident that 6.4T is going to be here, and then 12.8 is going to follow, and it's just going to keep on going.
I like the way that you talk about that. By looking in the past, we can look into the future.
That's right. It just gives us, track record of what's already been done, all right? And the people in the minds came together. Yeah, the confidence. The people in the minds came together to do it. So why not? That's right. What's preventing us from doing it again?
That's so great. Okay, good. And then let's go back to that. Let's zoom out and talk about ROI. What are the benefits in investing in testing, emulation, and optimization across AI network fabrics?
Yeah, I think there are multiple benefits. If you look at, doing the different components and the silicon, it's time to market. These times, AI times time to market is worth a lot of money. Then it's, how do you get your designs done with the least amount of respins? How do you do silicon and optics combined together at the same timeline, I think those all translate in time to market.
Yeah,
And
absolutely. And what I'll add to what Joachim said is, if you look at AI operators today, if you ask them what's the biggest challenge, a lot of them might say power, right? Because power is very constrained right now for these AI data centers. But there's another key thing that we're starting to come to terms with, which is when a lot of massive AI jobs are being run in these data centers, what these operators are seeing that is sometimes up to 50% of the time, the GPUs are idle, right? They're not doing anything. And these are very, very precious resources that, they're spending billions of dollars on. And you don't want these things to be sitting idle. So I think, using some of our emulation capabilities to replicate what happens in a production data center in a lab, we're able to, provide much deeper insights as well as the measurements that pinpoint where the bottlenecks are that help these operators then run their data centers more efficiently, more optimally, so that they can extract as much ROI as possible from the huge capital investments that they're making in building out these data centers. So I think, as Joachim was saying, there's many aspects to this entire runway. And we are participating from early stage, semiconductor, design, all the way to the operators rolling out these data centers. And we participate in every intermediate step along the way to enable and accelerate innovation.
And even if you have the system optimized, on a system level, you need to scale the data centers in production as well. And having high yield, good throughput, but also making sure you don't have any escapes, because failures in the field are very expensive.
They're very expensive.
And then that's a big ROI on test as well.
Thank you both. Lots of information there. Great looking forward to the future, and wonderful reflection on all the exciting technologies going on now.
Thank you for having us.
Thank you for having us, Michelle.
Thank you.
That wraps up episode 2 of AI Unboxed. We hope you found today's discussion on high-speed interconnects and software-defined networking helpful as you think about scaling AI networks for the future. Thank you for joining us and for the great questions. We may not get to all of them live today, but our experts will follow up with you by email. See you next week, where we explore Agentic AI and Ultra Ethernet, the technologies shaping the next era of artificial intelligence.